Today, we are diving into DINOv3 from Meta AI. It's a model that's part of this incredible quest to teach computers how to see. But this whole field hit a really bizarre wall, a place where making the AI models bigger and training them for longer actually made them worse at seeing details. DINOv3 doesn't just fix that problem, it completely smashes right through it.
Okay, so take a look at this. This AI can perfectly outline the elephant in the photo. Pretty cool. But here's the truly mind-blowing part. It was never ever taught what an elephant is. It figured this out all on its own, just by looking at millions of random, unlabeled images. So how on earth is that even possible? Well, the answer is this powerful idea called self-supervised learning.
Self-supervised learning, or SSL, is kind of like giving an AI a giant, endless library of photos with zero captions. To learn anything, the AI has to make up its own games, its own puzzles. For example, it might take an image, digitally tear out a chunk of it, and then try to predict what should go in that blank space. By doing this millions and millions of times, it's not just guessing, it's actually learning the fundamental rules of our visual world, what shapes fit together, what textures look like, and how objects are even formed in the first place. But this whole approach created a super weird problem, something called a scaling paradox. See, in the world of AI, the golden rule is supposed to be that bigger models with more data and more training should always perform better. But with these vision models, the exact opposite started to happen. As they scaled up, they actually got worse at seeing. And this is what that paradox looked like in practice. When models like the predecessor, DINOv3, were scaled up, yeah, they got better at global tasks, correctly identifying the main subject of an image, like saying, that's a dog. But at the exact same time, their performance on dense tasks, anything that requires super fine-grained detail, like outlining every single object, started to drop. The smarter they got at seeing the big picture, the more they forgot the little details. And this wasn't just a small hiccup. The researchers themselves pointed it out in their paper, saying that the model's performance on details would gradually decrease over time. This flaw basically put a hard ceiling on how powerful self-supervised vision could ever really become. And you can literally see that degradation happening right here. The image on the left shows the model's focus early on in its training. It's sharp, it's clean, it's localized. But look at the image on the right. After much more training, that focus becomes this noisy, degraded mess. The model is literally losing its ability to distinguish the fine details that make up the image. So the big question is, how do you fix an AI that actually forgets details as it gets smarter? Well, the DINOv3 team came up with a really elegant solution to anchor the model's knowledge and stop this degradation dead in its tracks. Their breakthrough is a technique called gram anchoring. It's a new kind of regularizer. And you can think of a regularizer as guardrails on a highway, but for an AI. It's a set of rules that keeps the model from veering off course and developing bad habits as it learns. And it works in 3 really simple steps. First, the team takes a snapshot of the model early on, right at that sweet spot when its vision for details is at its sharpest. Second, that snapshot becomes a permanent reference point. They call it the gram teacher. And finally, as the main model continues to learn and grow, the gram teacher is always there, constantly guiding it, reminding it of that sharp, detailed foundation so it never loses its way. And the result? It is absolutely night and day. On the left, you see the noisy, messy features of a model trained without this technique. And on the right, with gram anchoring applied, the clarity is just completely restored. This technique effectively repairs the model's vision, allowing it to get bigger and smarter without forgetting the fundamentals. All right, so the idea is clever, but does it actually deliver in practice? Oh, yeah. The results are definitive. DINOv3 didn't just solve the scaling paradox, it set a whole new state-of-the-art for performance. Let's just look at the scores on a really tough benchmark called AD2K, which is all about how well a model can segment fine-grained details. The score is called MIOU. All you need to know is that higher is better. So the previous model, DINOv2, got a 49.5. A competitor model hit 53. DINOv3 just blew them both away with a 55.9. And looking at this chart, that jump in performance isn't just a little step up, it is a significant leap that puts DINOv3 in a completely different class when it comes to understanding detailed images. That's a 6.4-point jump over its own predecessor. Now, in the world of AI benchmarks, an improvement that large isn't just a win, it's a knockout. It is a massive signal that a major breakthrough has just happened.
So look, this isn't just about getting higher scores on a leaderboard. The goal here is so much bigger. It's about creating a single, incredibly powerful, and versatile foundation for all kinds of computer vision tasks. The project really had 4 main goals. First, to create a single frozen model that could be amazing at tons of different tasks without needing to be retrained. Second, to achieve absolutely superior quality on those really difficult detailed vision tasks. Third, to release not just one giant model, but a whole family of them for different needs. And fourth, to build all of this into a new universal foundation for the entire future of computer vision. And its impact is already incredibly clear. DINOv3 is being used right now to analyze complex satellite data to estimate forest canopy height on a global scale. I mean, think about that. That's a level of environmental analysis that was basically science fiction not too long ago. Its power for object discovery is just as impressive. Without ever being told what a plant or a pot is, the model can find and isolate them perfectly. This is the core promise of self-supervised learning, and DINOv3 is just absolutely delivering on it. Another key strength is its stability across a huge range of image resolutions. So whether it's seeing a tiny little thumbnail or a massive high-definition photo, its understanding of an object's core features stays sharp and consistent. And this is vital for any real-world use, where image quality is never guaranteed. And this gets back to that idea of creating a whole family of models. The researchers took all the knowledge from their massive 7 billion parameter flagship model and distilled it down into a whole range of smaller, more efficient versions, from small and base all the way up to large and extra large. This means developers can choose the exact right size tool for their specific needs, whether they're running it on a laptop or on a massive server cluster. Look, DINOv3 is a fundamental step towards AI that can perceive the world with human-level detail, and it's doing it without our direct instruction. And that leaves us with a really provocative